Hello everyone, I am Anjali Dikshit, a PMRF Fellow in Department of Earth Sciences, IIT Kanpur, and welcome again to my lecture series, Seismic Inversion and Interpretation. So today's lecture will be based on seismic inversion. So the first question that comes into anybody's mind is that why seismic inversion is important and why do we do it, right? So So the main objective of the seismic inversion is to identify the subsurface structure or the rock properties. Now anyone can ask that we can get from the seismic data, as I discussed in my previous lecture that through seismic data also we can understand the subsurface configuration. Yes, we can do to some extent, but to get more level of confidence where we are more interested in knowing the earth's rock property, for example porosity, permeability, saturation or acoustic impedance, through which we can understand that when the lithology is changing and what type of lithology it could be, or if we are interested in identifying the oil and gas provinces, so what are the reservoir, we can do the reservoir characterization using the seismic inversion only, because this information will give us the quantitative information in which we are interested in. So to summarize whatever I have spoken till now, so this figure I think will give you more crystal clear idea about the seismic inversion. So let's understand this figure. Let me start my point. Okay, so suppose this is the lithology where you carried out your seismic survey, which is varying with depth. Okay, so for this particular lithology, it's there is corresponding acoustic impedance response. And now what is acoustic impedance? It's a product between the rock density multiplied by the rock velocity. That you can also understand from this response. For example, for this particular lithological unit, your acoustic impedance responses is changing, and when you are going towards the next lithological unit, your acoustic impedance responses is going in the positive direction, which imply that either your density or your velocity is getting increased with depth, and when again we are going to the next lithological unit, your acoustic impedance is it's moving towards it's getting little less as compared to the previous unit. So for this acoustic impedance, we can easily get the reflection coefficient series, and how do we get the reflection coefficient is using this formula, which is the division of difference of acoustic impedance and the sum of acoustic impedance of two lithological unit. And you can see that whenever our acoustic impedance responses is changing at particular boundary, we are getting the positive reflection coefficient, and when we are getting the negative, when our acoustic impedance responses is getting reduced, we are getting the negative reflection coefficient. So what happens, during the seismic survey, as I discussed earlier in my lecture, we send the source wavelet using the source, which could be a thumper or vibrating gun. So when this source wavelet get convolved with this reflection coefficient series, we get the seismic response. So from that seismic response, we are interested to know the acoustic impedance response, which is the intrinsic property, intrinsic rock property. So that's why this whole process is called as an inversion, because we have the forward result, which is our acquired seismic data, but we are interested to know about the subsurface lithological model. So now there are ways to calculate the seismic inversion So mainly there are three methods. First is the direct inversion method, where we used the physics based operator. So what this operator does is that you give the seismic data and it will by applying the physical laws, it will give you the inverted model data. And this model could be your acoustic impedance or the porosity and permeability, like the inverted property in which you are interested into. Accordingly you can design the operator, but it comes with a limitation, and the limitation is that that we all are aware that the acquired seismic data is contaminated with noises. So to encounter the effect of this deleterious noises in advance, it's very difficult to achieve. So that's why there is another scheme available for this inversion, is called as a model based inversion method. So here we first assume one initial model of our earth, and then we apply the forward model and generate a synthetic data. Then we try to compare or try to see the mismatch between our observed data and the synthetic data. So to reduce this mismatch, we again try to update our initial model so that we can minimize the mismatch between both the seismic data. So that's why this process is considered as optimization process, because we keep on updating our model to reduce the objective function, which is a norm between the synthetic data and the observed data. And apart from this, there is another scheme that is available, is called a linear inverse method. So as its name suggests, that linear, so we are assuming that there is a linear relation exists between the data and the model parameter, which is not completely true, because we know that there is no linear relation exists, but we assume that to some extent, like for example, for the case of small angles reflection, this linearity holds to some extent, and we can apply this linear inverse method in these scenarios. So to get the solution using this linear inverse method is by applying the least square method, by applying the singular value decomposition, or by constraining the solution. So for constraining the solution, what we are trying to achieve is that as we know that this every geophysical inverse problem is non-unique because of the uncertainty associated. For example, the noise effect, and then we are not completely aware about the source wavelet nature. So that's why it's a non-unique problem. And also the assumptions that we use, that also brings kind of noise into the data. So due to all these factors, what we try to constrain the solution space or the model space. So for constraining the solution, there are several techniques available. For example, by giving the prior information, by applying the positive constraint or the inequality constraint, and the most famous technique for this is the regularization. So in regularization, what we do, so in this when we apply the regularization, our total misfit function comes in this form. So in the normal misfit function, you will get only ED, and ED is the norm between your data, your synthetic and the observed data. But whenever we are applying the regularization, the second terms appear, where alpha is the weighting term and EM is the norm between your model parameters, like the one that you extracted from your data and the one that you can get it from your well data. So this is a complete form in case of regularization. And so now you will get the idea, like brief idea about the regularization, and I'll discuss this regularization in more detail in the lecture that I'll prepared for completely for regularization. So here you can also see that we are applying this weighting term specifically to the model misfit term. So because we are more interested into constraining our model space, we are not trying to constrain our data space, because our our interest is to know the model parameter. So that's why we are trying to constrain the model parameter as per the knowledge available with us. So the whole motive of applying the regularization is to get the good approximation of the desired solution, or knowing the desired model property. So moving forward, let us understand about a little bit about the scenario where the relationship of linearity doesn't hold. So in general, the inverse problem can be written like this, where D is the seismic data acquired and G is our forward model, and not forward model, sorry, it's forward operator, and M is a model parameter in which we are trying to do this inversion. So as I discussed earlier, that by splitting this equation, this complete form, into sets of linear equation, and that can be solved using SVD and least square method, which is a single step process. Like you will solve the equation and you will get the solution. And so the problem exists when so this can be applied when the forward problem is linear and when the weak non-linearity holds. But what if there is no linearity holds, like we are doing the we have the data where reflection coefficient which has a reflection angle very high. So there this assumption of linearity doesn't hold. So in that scenario, our non-linear objective function can be written in this form, where WD is the another weighting parameter, and if we apply the model constraint as I discussed in the previous slide, in the regularization slide, our objective function got modified, and this is the complete objective function. And this complete objective function can be minimized using the optimization process. Now let's understand what is, because we are trying to minimize the difference between our synthetic and the observed data as much as possible by changing our initial model, or by updating our initial model as much as possible. So this is so in this figure, this is some this is the objective, some hypothetical objective function, and it has only, here we consider only one model parameter, and so this is the x-axis is representing the one model parameter, and error is representing like in the previous slide it was so error is our total E term in that our total objective function. So here you can see there are it's a multimodal objective function where lots of local minimas are present, but we don't want our solution to get converged at the local minima. We want to achieve the global minima so that we can reach as close as possible to the real Earth scenario. So for that, a very famous optimization scheme is the local optimization, which is a kind of deterministic method, because in this scheme you first assume one initial model, and then by applying the gradient descent or conjugate gradient descent, it try to achieve the point where we get the zero gradient. But it's this technique is very prone to the position of your initial model. For example, if you have chosen your initial model over here, then you are in a very good position. You will reach the global minima once you will get the zero gradient. But what if you choose your initial model over here at second position? So while reaching the zero gradient, you are achieving the local minima but not the global minima. So to elevate this problem, there is another kind of optimization scheme, which is a global optimization, which is independent of this initial model, because it search through entire solution space. But because as it's searching through entire solution space, this technique is highly computationally extensive, and we'll discuss about all these like both the optimization scheme in detail in the later lectures. Thank you for listening. Hope you have understood all what I have taught till now. Thank you.